Alright, hello everybody, and today I'm going to be proving Euler's formula right here, which says that the cosine of some angle plus I times the sine of some angle can be written as e to the I times that angle. So this is just a polar representation of complex numbers, and we're going to be proving this fact using the Laplace transform. And why exactly the Laplace transform? Well, it's nice in the sense that we can turn all of this periodic and exponential junk into more nicer algebraic expressions we can work with. So to get started, let's just replace all these thetas with t's. It really doesn't matter what we use, but for our purposes of using Laplace transform, it would be nice to work with t. And let's just forget about this e to the it right now. We want to work with this left-hand side a little bit. So let's take the Laplace transform of cosine of t plus I times the sine of t. And you see, the Laplace transform is a linear operator, so we can actually split this addition inside of here into the sum of two Laplace transforms of cosine of t, close that off, and then now we can bring the I up because it's just a constant, and we have the Laplace transform of sine of t. Okay, and if you refer to your Laplace transform table, you'll know that the Laplace transform of cosine of t, that's exactly s over s squared plus the constant in front of the t squared, but the constant in this case is just 1, so we'll just add 1 squared, which is 1, and then now we have I. Laplace transform of sine of t, that's exactly the constant in front of the t, but that's just 1, so we'll just have 1 in this case, over s squared plus that same constant but squared. So now pretty much all we're doing is we're just working with fractions. Let's just move this I up to the top here. And notice that we have a common denominator right here. So why not combine the two fractions together? So we'll get s plus I over s squared plus 1. And maybe you see it, we can actually simplify this a little bit. Because notice this positive 1 right here. Adding a 1, that's the same as subtracting a negative 1. But what is negative 1? We can actually express negative 1 as I squared, so this becomes s squared minus I squared. And now on the denominator, we actually have a difference of 2 squares, so we'll expand that a little bit to get s plus I over s plus I and s minus I. And the nice thing is, this numerator and this factor right here will cancel out, and what we're going to get is 1 over s minus I. And now we can actually take the inverse Laplace transform of this to get back to our t domain. But if you have a look right here, notice that if we cover up this negative I right here, the inverse Laplace transform of 1 over s, that's exactly 1. But because our s is being shifted by I, we actually have an exponential shift in our t domain. So taking the inverse Laplace transform of 1 over s minus I, that would actually result us in an exponential of something times t. And what is that something? Well, if we have s minus some constant, well, that coefficient of t will just be that constant itself. So the inverse Laplace transform of this thing right here is exactly e to the it, and that's exactly the result that we're expecting right here. So that turned out quite nicely. So yep, that's pretty much the proof of Euler's formula using the Laplace transform.